All right, lesson 6, gravitational fields. So gravitational force is an action at a distance force. So that's why if you hold a pen up in the air and you drop the pen, the earth pulls on the pen, even though the pen and the earth are not touching. Okay, another example of an action at a distance force is the magnetic force. So here we have a bar magnet, and that bar magnet is able to attract a steel object like a screw, and the screw is not touching the magnet, but that force is still there. What we would say is that this magnet has a region of influence around it. Now you can't see this region of influence, but it's there. If a metal object, like this screw, enters that region of influence, it gets pulled towards the magnet. So the idea is there's a magnetic field here. That region of influence is called a field. And the field is actually what causes this force. So there's a region of influence around the Earth as well, but instead of being caused by a magnet, it's being caused by gravity. So if you look at this picture here, these arrows are supposed to be showing the region of influence. Now you can't actually see them, they're invisible, but if you could see them, that's what they would look like. This region of influence with all of the arrows in it is called a gravitational field. If an object enters the Earth's gravitational field, that object will be pulled towards Earth. So if you put a pen in Earth's gravitational field, the pen will feel a force pulling it towards Earth. And the idea is it's actually this field here that causes the force. Now it's important not to mix up fields and forces. The field does cause the force, but the field and the force are not the same thing. The force is the actual push or pull that the pen feels. The field is what we use to describe this area here that surrounds the Earth. So, question for you to think about, which planet has a stronger gravitational field, Jupiter or Earth? You might make a prediction that it's Jupiter, but how would you actually test that? If you had the ability to go to Jupiter, what's an experiment that you could do there that would confirm that Jupiter's gravitational field is stronger than Earth's? Well, something that scientists do is they use something called a test mass. So a test mass is a mass of 1 kilogram. And what you can do is you can take your test mass and drop it. So let's say that you could go to Jupiter, you bring your test mass with you, and you drop it. Assuming you have all the right measurement tools, you would find that your test mass accelerates on Jupiter at 24.8 meters per second squared after it's been dropped. Or in other words, we'd say the acceleration due to gravity on planet Jupiter is 24.8. If you do the same experiment here, if you take something that is 1 kilogram and you drop it here on Earth, it's still going to accelerate, but at only 9.81 meters per second squared. What we can infer from this is that Jupiter must have the stronger gravitational field because objects dropped there are affected by gravity more than they are here. Now, what scientists decided to do is they said, well, why don't we just use these numbers that we already have, this 24.8 and this 9.81, and just use those as our gravitational field strength. So instead of having to come up with another quantity that we have to have calculations for, we're just going to reuse acceleration due to gravity. So gravitational field strength is equivalent to acceleration due to gravity. So what that means is I can say the acceleration due to gravity on Earth is 9.81 meters per second squared, or equivalently, the gravitational field strength on Earth is 9.81. So notice it's the same number. Now, to communicate what we mean, sometimes we change the units. So instead of writing meters per second squared, we'll write newtons per kilogram. But what I want you to notice here is that a newton per kilogram is really the same thing as a meters per second squared, because a newton is a kilogram meter per second squared. And if you divide that by a kilogram, then the kilograms cancel out, leaving you with meters per second squared. So 9.81 meters per second squared and 9.81 newtons per kilogram are exactly the same thing. It's just that often when we're doing kinematics, we'll stick to meters per second squared. And when we're doing gravitational field strength calculations, we'll use newtons per kilogram instead. But you're free to use whichever one you prefer. So calculating gravitational field strength. So this example says a 50.5 kilogram person weighs 1,250 newtons on Jupiter. What is the gravitational field strength on Jupiter? Well, gravitational field strength just means little g. And we already have a formula for little g. It's Fg equals mg. Now that we've introduced capital G, which is the gravitational constant, that's 6.67 times 10 to the negative 11 number, it's important to distinguish between little g and big G, by the way, so make sure you don't mix them up. But yeah, gravitational field strength is little g. So I can just take the formula here and rearrange for it. I'm going to do Fg over m. Now remember, weight is really Fg. Weight and Fg are synonyms. So I just have to do 1,250 newtons over 50.5 kilograms, and that gives me 24.8. I could write that as 24.8 newtons per kilogram, as you can see in the formula there, or if I prefer, I could write it as 24.8 meters per second squared, same thing. So we now have two different formulas for calculating Fg. We have this one here, Fg equals mg, and we also have this other one, Fg equals big G, ma, mb over r squared. Yeah, you'll notice here I have changed the variables. So instead of calling this ma, mb, I've changed it to mo and mp. And the reason why is so that we don't get confused in just a second. MO is going to stand for object, so the mass of the object. MP is going to stand for the mass of a planet. So for example, if I wanted you to calculate your weight right now using this longer formula, MO would be your mass in kilograms, and MP would be the mass of the Earth. Or you could use this shorter formula here. MO would still be your mass in kilograms, and then G would be 9.81. You should actually pause the video and try that. And what you'll notice is you're going to get the same answer whether you use this formula on the left or this formula on the right. So Fg is the same both times. It's just how you calculate it is different. So again, MO is for the mass of the object, and MP is for the mass of the planet. What we're going to do is we're going to combine those two formulas together. So we're going to take, because they're both equal to Fg, we're going to take MOG and GMOMP over r squared, and we're going to make them equal to one another. And what I'd like you to notice is that MO shows up on both sides of the equal sign. So that means I can divide both sides here by MO, and MO will cancel out, leaving me with little g equals big G times the mass of the planet over r squared. So what this formula allows me to do is it allows me to calculate the value of little g, which is the gravitational field strength, on a particular planet. As long as I know the mass of that planet and r, which is the distance from the planet's center, then I also know capital G as well, right? Because it's a constant. As long as I know those three values, I can find out what little g is for any planet that I want. So let's start by seeing how that formula works for Earth. So it says, use the formula above to calculate the gravitational field strength on Earth's surface. You will need to use your data sheet. So these are the numbers that I pulled off the data sheet here. So the radius of Earth is 6.37 times 10 to the 6 meters. And the mass of the Earth is 5.97 times 10 to the 24 kilograms. This is my sketch of the Earth here. That's the radius of the Earth. So it's measured from the center of the Earth out to the surface of the Earth. And if I want to calculate gravitational field strength, which is little g, I can use the formula that we just derived there. So I can do 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 over 6.37 times 10 to the 6, and don't forget the square there. And when you do that, you do get 9.81 meters per second squared, exactly as we would expect. So now let's do another one with a little change here. So it says the International Space Station orbits 420 kilometers above the surface of the Earth. Determine the gravitational field strength aboard the space station. So I've drawn a picture again. So this is the Earth. From the middle of the Earth out to Earth's surface, that's the radius of the Earth, which I'm calling RE. And then the space station is 420 kilometers above the surface of the Earth. So from right here, where I'm wiggling my mouse, out to the space station, that's 420,000 meters. Remember, we want to work in meters and not kilometers. This r in the formula is the total distance. So it's always the distance from the middle of the planet out to the object. So r is really re plus 420,000 meters. And so I went ahead and did that, and I got 6.8 times 10 to the 6 for the value of r. And then I threw it in this formula here, and I got little g at the location of the space station is 8.57 newtons per kilogram. So what I'd like you to notice is little g is only 9.81 when you're at the surface of the Earth or close to it. When you move really far away from Earth, like at the location of the space station, g is lower. So you should only be using 9.81 in calculations that take place on Earth's surface or close to Earth's surface. If it's something even, a little bit out in outer space, you need to calculate little g before you do anything else. Okay, example 9. The planet Mars has a mass of 6.42 times 10 to the power of 23 kilograms and a radius of 3.38 times 10 to the 6 meters. How much would a 50 kilogram person weigh on Mars? How much would that same person weigh on Earth? So what I've decided to do is I said, okay, I'm going to calculate the gravitational field strength, or the acceleration due to gravity, because it's the same thing, on Mars. And so I'm using the formula here. I've put in the mass of the planet. So what can be kind of confusing for students is we're being given two masses here. We're being given the mass of Mars and the mass of the person. Here, remember, in little g equals big G mp over r squared, mp is the mass of the planet. So that's 6.42 times 10 to the 23. And then here, the distance is just the radius of Mars, which I'm calling rm, because the person is going to be standing on the surface of Mars. So the radius of Mars is the distance from the middle of the planet to the person. So that gives me a little g value of 3.748 newtons per kilogram on Mars. But then remember, weight is actually Fg. So I have to do one more step. Fg equals mg. So now I can take the person's mass and multiply by the gravitational field strength. You'll notice their kilograms cancel out, leaving me with a number of newtons, which after rounding, I get 1.9 times 10 to the 2 newtons as the person's weight on Mars. Now, on Earth, I can just jump right to this Fg equals mg step because I know that on Earth, little g is 9.81 meters per second squared. So after rounding here on Earth, I get 4.9 times 10 to the 2 newtons. Okay, there's a question here for you to try. I've put the answer here for you, so you should be getting 685,131 meters before you round. My hint for you is that before you try this question, you should draw a diagram. And if you try it, but you can't seem to get this answer, what I'd like you to do is send me a picture of your work by email, and I will send you back some feedback. But please draw a diagram before attempting it.